Hello, my name is Marianne Su, and I am presenting the importance of the single-span task formulation to extractive question answering. In this project, we are working with extractive closed-domain question answering, a subfield of machine reading comprehension. In this subdomain, a machine must answer a question by extracting the answer as the span of a given passage. For this project specifically, we are looking at questions with multiple answers, or multi-span question answering in particular. On the left is an example from the Stanford question answering dataset, or more commonly known as SQUAD, which is a single span dataset. Each question, as you can see, has only one span from the passage that answers the question. On the right is a multi-span example from the discrete reasoning over paragraphs, or DROP dataset. Unlike the left example, this question has more than one answer that can be found as multiple spans of the passage. In this project, we are testing how deep learning models perform on multi-span questions to see if existing single-span models can identify these multiple spans, or if they're only finding one high-quality answer. So improving question answering will increase efficiency. For example, if a user poses a question and the machine cannot find the answer, the user then has to spend their valuable time looking for it. Identifying the current structural limitations of existing models will help improve the applications of question answering, such as chatbots and dialogue systems, and make the question answering process more efficient. A variety of fields can benefit from more refined question answering, not just certain industries. For example, a relevant question today would be like, which 3 states have the highest COVID-19 cases? Even in daily life, machine question answering plays a key role, and developing it further can help many people around the world, not just on an industry level. In this project, we construct a new dataset specifically for multi-span question answering with questions with multiple answers. Unlike previous question answering datasets, which are primarily single span, our new dataset is entirely multi-span. While specific models like the multi-type multi-span network have already been made to tackle multi-span question answering, in our case, we are testing the more standard models like BERT and BERT-based models. And we want to see if these existing models pre-trained for single span question answering can find these multiple quality answer spans when faced with multi-span questions, or if they're finding only one superior answer while the rest are unsatisfactory. Because the majority of previous datasets are composed of questions with single span answers, we collect all multi-span examples from the existing DROP and UseQA datasets to make a new all multi-span dataset, which consists of almost 30,000 question answer passage triplets. The graph on the right shows 60% of those 30,000 examples, where the inner circle shows the top 10 first words of the questions, and the outer ring shows the top second words. We then run a base and a large version of BERT, RoBERTa, and ALBERT models pre-trained on SQUAD, a single span question answering dataset, on our new multi-span dataset. Because these models were the most downloaded ones from the Hugging Face Models website that satisfied our single span pre-training requirements, we used Albert Extra Large instead of Albert Large since it was the one available. For the extraction, we implement a naive greedy approach and extract the top non-overlapping spans with the best scores. The number of true answers dictated the number of spans that we extracted. So, for example, if there were 2 true answers listed from the original data set, we would then extract 2 spans to be our predicted answers. After obtaining the predicted answer spans, we then calculate the exact match, precision, recall, F1, and blue 1 score. And because our answers are short, normally 1 or 2 words, you can only look at 1 word or engram at a time. So we are deviating from the standard blue 4 evaluation due to the length of our spans. In this performance analysis, the class 1 metrics represent evaluations between the true and predicted answer spans on a character level. We find that the larger models mostly perform better than their base counterparts, with RoBERTa Large having the most consistently high scores overall. Certain models do very well in certain metrics. For example, BERT-based has the highest average exact match, and Albert extra large has the highest average F1 score. However, we also notice that the rest of the metrics for these two models are worse. On the other hand, RoBERTa, and particularly RoBERTa large, has the most notably high scores overall. For this evaluation, we consider recall to be the most important. If the recall is high, then the predicted answers are getting the majority of the true answers, and the models are able to find the correct answers, which is what we want. We can compare our scores to the exact match and F1 scores of the multi-span subset of the original drop dataset, which was run on a BERT-based model. We see that our exact match is much higher, but our F1 is similar but a bit lower. One reason for this is that the multi-span examples from the drop dataset only make up around 20% of our new multi-span dataset. And while MuseQA was not run on a BERT-based model, we can see that our models had lower scores. However, this is expected since most of the original drop and MuseQA datasets were composed of single-span questions. And while we cannot definitively conclude that that the model's performances are not affected by the change of task, so from single-span to multi-span question answering, we can see from our results that the models are capable of adapting to multi-span question answering to a high degree, as shown by RoBERTa large's consistently high scores. One reason for this may be due to its alternate training strategies, and the models overall do not perform as well in multi-span questions as they do on single-span ones, but our evaluations do show that the models are not structured to return only one high-quality answer. Using this knowledge, these existing models can be modified to hopefully improve machine question answering. Potential future work includes fine-tuning a model specifically for multi-span extraction and implementing a more robust extraction method rather than our naive, greedy approach. In addition, more work could be done using more standard evaluation methods. Another prospective project includes studying performance on subsets of the new multi-span dataset, such as the what, who, where, which question subgroups. And we hope that future researchers will use the new multi-span dataset created in this project and use our evaluations to discover the current limitations of question answering models and determine how to improve them. I'd like to thank Rahul for mentoring this project and to the Summer STEM Institute for providing the opportunity to conduct this project. Thank you for your attention. Are there any questions?